No. Oh. No. Hello everyone, and thank you for joining me. My name is John Stevenson. This is Practicalli, and today we're going to continue with some more Codewars challenges. I chose one at random, and it just happens to be one that's a little bit mathematically orientated, and I haven't quite solved it, but I have some ideas about how to do that, so hopefully we'll get most of it solved. I have solved some of the easy paths, but the actual meat of the thing, there's a few different ways we can explore how to solve that. So there will be some live coding hacking about halfway through. But let's see. And if you have any suggestions about what we're doing or any feedback, please feel free to add them into the chat as we go along. Oh, thank you. Yes. It will be there forever, as long as I am. The flag, there we go. That's us. That's a star. Okay. Just a bit of commercial. So Practicalli for me, so I've got all the screencasts and videos I'm doing. I've just finished doing some screencasts for somebody else, so I can start working on mine again and try and make some. So I'll do some playlists with some nicely constructed screencasts of using Clojure and doing little exercises in Clojure as well. So they'll be more scripted rather than these study groups, these weekly study groups, which are very ad hoc and done at the last minute. But you get to see my thinking process and hopefully interact with that process as well. And if you want to get in touch with me, then Slack is a pretty good channel to do so. You can either contact me on the Practicalli channel on the Clojure in Slack. And if you don't have an account, you can sign up here as well. You can send me a DM as well if you don't want to ask questions publicly. And you can always reach out to me at john@practical.li as well. Okay, let's go. So the challenge, which I put the link in the chat as well, is this maximum subarray sum, which at first I thought was fairly simple until I actually understood the problem and then realized it was a bit more challenging. But it's an interesting way to process a sequence, but trying to do it in a very functional approach. So if you haven't seen Codewars, then we've got the we've got the instructions that tells us what to do, and we've got we need to write our solution, and we've got some simple tests as well. And I've created a project in just on the command line, just using the Clojure-CLI tools and CLJ new. I've just created this project, and I put in the solution to be filled in, and also some tests, and I've also added a few tests. So this is the test that's in the Codewars sample test, and this red highlighting means that test hasn't passed yet. But I've done tests. I've run these tests. These are tests I've written just to test the all negative numbers. So if you have a sequence where all the numbers are negative in the sequence, then you just return 0. So that's a fairly simple test to do, and I managed to write something to get that passing. And if you've got a sequence where all the numbers are positive, then you just add them up. So again, those are two very simple paths. The real meat of the challenge is in this, trying to find a sequence within this sequence. So like trying to find a subsequence that is that gives the biggest value. So you can kind of like add them all up, or just add a couple of numbers up, but they have to be sequential. So we're not adding 2, and so we can't just add the biggest numbers up because they're not sequentially they're not grouped together sequentially. So we compare like 2 and 1 together, or 1, 2, 1, 3, and 4, and whichever of these subsequences gives the biggest number, then that's the number that we want. And in this case, it's I think it's they give you the example to pass the test, and it's these these 4 numbers. When you add them together, they give you the biggest value. So the 2 ones cancel each other out, and you've got 6 altogether. Yeah, and I think, yeah, so you can, if you wanted to, you could cheat passing you could just put the value in max sequence and then run the sample tests, and yeah, they run and they'll pass. But if we do an attempt, then I'm pretty sure that like lots of other ones are going to fail. But it gives you an idea about what it's actually testing, and you could pull out all this test data in there as well, because it's giving you what it's trying to do. That's a good idea, actually. Whee! So that's a big one. And so I could also put that into the test there as well. Boom. Whoa, that's big. Oh, that's huge. I'm going to comment that out for now and come back to that. Let's see. Boom. Because that's huge. There we go. So we're just going to use this this test really to see if we can get an answer, and then we can try it on a bigger test as well. So let's switch back to the code. So we've run so we've done some unit tests already. So one of those was to find if all the numbers in the sequence are positive, then we could just add them up. So how do we do that? Well, there's a nice predicate function, and a predicate function is just a function that returns true or false, like a boolean value. And by convention, we put the question mark at the end of those function names, just to give you a visual clue that it's a predicate value. So you're going to get either true or false back from this. And it just helps in the reading of Clojure. It would still do the same thing if it didn't have the question mark, but it makes it easier to read and to understand for yourself and somebody else who's looking at this code. So let's see. So you can see here, if we do pos on a minus number, then we get false. If we do it on a positive number, then we get true. Does it work on there? Yeah, and it also works on. So pos also works on numbers. If you want an integer, then there's a pos-int version, which I think is just pos-int. Yeah, so there's a pos-int version, so it will just check specifically for not just a positive number, but a positive integer. So you can also filter out things like decimal numbers if you wanted to. I wonder what that does actually with a decimal number. Yeah, it's false. Okay, so it's just, again, it's just a predicate. It's just returning true or false. Cool. But it doesn't like it doesn't like non-numbers. So if you pass a string or a keyword, then it goes bleh. It definitely sees that as an error. So we can map pos over our data. So this is our data from the sample test. And you can see it's going over and pos is acting on each of those individual values, returning true or false, true or false. So my initial idea was that if you map pos over them, then you could use and to see whether they were all true. And if they're all true, then you're going to get true. but if one of them is false, or one or more of them is false, then you're going to get false. So if you just use the AND function, well, it's a macro, but we can use it as a function, and it's going to take one or more values, and if they are both true, or if all the values are true, then it's going to return true, but if one of them or all of them are false, then we get false. So I thought, oh yeah, that'd be quite simple. But then I forgot that AND is a macro, and it can't work on a collection. It's only working on individual numbers, or individual values, sorry. So if we wanted to AND this together, we're not actually getting a... Oh, that's interesting. It's just returning the value. So we can't... so if we wanted to apply AND to all of these values, we'd have to use something like apply, which puts the AND into the right expression to call a specific value. So apply AND would be the same as doing and then false, true, false, etc. Oops. So with apply, we can apply it to as if we'd rewritten it so that AND went into here. But we can't use AND with apply because AND is a macro, and so macros have some limitations when you want to compose them together with functions. And macros are very useful for expanding the language and reducing any boilerplate code that you might have to create, but they're not as composable as functions, unfortunately, so we can't really use AND in this situation. So I had a little Google around to see what else we could do, and instead of AND, I found every. So that actually, I think there was in the page for AND, I think there was an example. Do we got AND in here? Yeah. So I think I went to AND, and I think in the bottom of here there was like a little note, here, saying that instead of using apply add, which won't work, then you could use this every entity, which does work. So it basically applies identity to every value, which just returns the same value. And so this is going to return true, false, true, false, true to every. And if every one of those is true, then I think it returns true. Yeah. So it returns true if predicate x is a logical true for every x in the collection. So if everything is true, then it returns true. And so here we're testing to see whether something is even. And so they're all even, so they're all going to return true. So then every returns true as well. Whereas these aren't even, and we get false. So that's quite cool. So we did every identity, and that worked okay. But it is a bit verbose. So we got that false. When we do it on the sample data, then we can see that not every value is positive. So we get the false results. So that's enough to help us skip over that particular data and pass it to another branch where we test to see if they're all negative. Well, actually, you can test to see if they're all negative, and then test to see if there's kind of a mixed number of values. But I also noticed that there was a nice thing called every pred. So every predicate, where you can actually chain predicates together. So it looked quite powerful. So we could actually do kind of things like number, odd on here to chain them together. So what it's going to do is it's going to apply number, and then are they all numbers? Are they all odd? And what it does is every pred builds up a function. It returns a function that's a combination of these two predicate tests. and then runs it on the data. So that's why we have this expression. It's every pred expression, and that's going to return a function, so that needs to be in brackets as well. So the thing that's returning needs to be in these outer brackets because it's returning a function. Hopefully that makes sense. We go to do we go every pred? We're actually going to open the source of that. We can probably see what it's actually doing. So this is this is a higher order function. So it's going to return a function that returns true if all the composing predicates return a logical true. So you can have a whole range. You can have a whole pipeline of predicates and do a lot of kind of sophisticated testing of whether all the data is kind of true or false as well. And you can you can use predicates that are built into clojure-cli, but you can also write your own predicates as well. So I thought that was quite neat. Where is it? Oh, that's stinky. I haven't actually looked at that. Oh yeah, you see. So when we call this, no matter how many arguments we pass to every pred, it's always returning this function definition. So it's returning this fn expression, which is then used to call with the data that we've got there as well. So this is a nice example of a high order function, and it's actually quite nice. And I mean, there's a lot of code in there, but it's relatively simple. It's actually just calling the boolean or every, depending on how many arguments you got. So yeah, it's quite a nice example of, if you've not used higher order functions before, it's a nice way to kind of delve into that a little bit deeper as well, I think. Okay, no questions so far, so let's keep going. So we've got every pred positive, so I think we could probably just use every or every pred. I'm not sure it makes much difference here. I've used every pred just because, I don't know. And then I can apply that as well. So I can apply every pred to here, and I get the false, which is the same as writing every pred inside the. Well, it's like basically flattening the so flattening the collection there. Yeah, so I think I can probably just do. I think I just got carried away with the excitement of learning a new function. So so we do every pred. Pause. Boom. And then if we do can we do the collection? Not sure if we need to do the thing in the collection there. Boom. Or if we see, oh yeah, that works. Cool. Oh, that's nice and simple. Yeah, because I don't think every is returning a function. I don't think it's a higher order thing in there. No. Yeah, so it's probably in this case, because if we're only using one predicate, then every seems to make sense. Whereas if we've got multiple predicates, then we'd use every pred to be able to combine them together. Let's have a look what every does. Yeah, every is blah blah blah. That's just metadata. So taking a predicate and a collection, and it's just doing a cond to see whether the sequence is empty. And if it's not empty, then we just get the first collection, and we're just recurring the pred function over the collection. Okay, yeah. So this is essentially like mapping whatever predicate we've got over each value in the collection that we've passed to it. Okay, cool. So yeah, every is a lot simpler. and probably all we need for this case, I think. But I've used every pred in the example. So I put this together as a max sequence, which is the name of the, it's the name of the function that we need to write for the Codewars. And we take in data, and we've just got a simple if statement. So we do the apply of predicates on the data. So if everything is positive in there, then we just basically add everything up, again using apply to add up all the data in the collection, and we can just return nil. And if we do that and then run the tests, go back to the tests, I've forgotten how to run the test for a second there we go. So it's passing all of these positive tests. It's failing the negative ones because we haven't done that bit yet. But yeah, and it's obviously failing this one because this is a mixed number of positive and negative numbers. So that one satisfies the positive tests. Which we can also see here. Yeah, so it just adds them up. So that's really simple. And then to actually make the other ones work, we just, instead of I put nil, I think. Yeah, I put nil in there just as a default. So that made the negative tests fail. But if I just return 0, then that's going to make the all negative numbers tests pass. Which it does, yay! But we've still got one, like the most important one still fails. But we're getting there. We're making progress. So if we were just testing for negatives, then that's and positives, then that we've kind of done that already. But the real meat of the challenge is to try and find a sequence that is producing the biggest value. And this is the tricky bit. So we could just add them up, and just here I've just kind of taken the first value off each time, and we get some values there, just as like see if there's like an obvious value that sticks out. So this one's close. This one gets 5, but all of these ones actually produce a value that's less than the value that's in our test, which was 6. So this isn't quite enough combinations to find the right subsequence. And so my thoughts were like either reducing function that builds the subarray, going through every combination of sequence, or a lazy generated sequential combination. So it goes through every single combination potentially as a lazy sequence, and then drops the sequence if it's less than the first one. I think the challenge is that if you're going through these values, then it's not an obvious. There's no obvious kind of way to discover which one is without testing all the combinations. Because if you add 4, so if you just take the sequence, start the sequence at 4, and then you just do 1, so look at the next one, see, well, that's going to be a less value, so that's no good. But if you actually add the next one on top of that, then you've got 5. So you have to kind of keep on going, even if your numbers are going down. So one option was to just generate every single sequential permutation of the data. My only concern there was that unless that was managed lazily, then potentially if you had a lot of data, then it would just, if you had a lot of data you were trying to analyze, then that could blow up your stack, your memory in your computer, and it might not be the most efficient way. But then this is a Codewars challenge, so I mean, we're not necessarily having to look for the most efficient way to start with. So I thought about just kind of generating well, how would I generate the above kind of thing? Because I don't want to type everything in, and that's obviously not going to work as a program. So I wrote a little thing that takes, it's called tails, a little function called tails, and this will use iterate. So it's going to iterate rest through a sequence. So we pass the sequence in, and iterate creates a lazy sequence, and so we're only going to generate those ones that we actually want. And what it does is basically just gets the rest of the sequence each time. So basically we're just dropping the first element off the sequence every iteration, and then we've got a condition to check to see how many to take. So we're going to take while. So we're going to take a certain number of values. Excuse me, and we're going to we're going to test to see if we should still be taking them with the seek function. So the seek, so the seek is our kind of like termination condition, because if we do rest on sequences, whether they be in a vector or a list, it doesn't matter. It's still going to treat them both as a sequence. So we'll get the rest of the values. Unfortunately, if you have rest of an empty sequence, it's going to return an empty sequence. So you potentially go on forever and ever and ever and ever. So you need to test for the empty sequence, and so you know when to stop iterating through that. Even though it's lazy, I mean, you still carry on iterating until you run out of memory if you've got nothing to tell it when to stop. So we use sequence. If you use seek on an empty list or empty sequence, then it returns nil. So that's fed into the take while, and that basically says, okay, well, it's nil now. I don't need to take any more. I can stop. And then it just folds everything back up into the main sequence here with all the sequences it's generated so far. So this is a little bit strange, but it's kind of a clojure idiom to use seek, because you can use empty on a vector or a list. So that's empty is true, but seek is, but then so you would need to kind of do not empty. Is that right? Yeah. So you'd have to do not empty to get false, and it's more of a convention to use seek instead of not empty as well. I wonder if that tells me, what's that telling me there? Oh yeah, there we go. And if you've got CLJ condo, it actually tells you that that exact idiom there as well. So it's using the idiom seek rather than not empty. So thank you very much, Bokdude, for helping me remember that. So CLJ condo is a linter that I have running constantly in the background. It just checks my Clojure code and gives me suggestions about what I should be doing or not doing, and just checking the syntax and so on, and where I'm not using things. So it's very, very handy in that respect. Okay, yeah. Let's comment that out. Oops. Okie dokie. So we did tails, and I did the reverse thing just using reductions as well. So just like, again, it's been a while since I did a reduction. So reductions is like reduce, but it's going to produce all the intermediate values. So if I just did, oh, there we go. I think I've got down the bottom there. Oops. Come on. My Vim-foo is failing me here. Did I put that there? Okay, no. So if I did, instead of reductions, So if I take that expression and just run it by itself, and instead of reductions, I do reduce conj, and then I'd need to use the actual data, which is there. There it is. So hopefully you've kind of had some experience with reduce. So if we reduce conj on here, then we just get the result. So we get the result of conjoining each of the values in our data with the sequence. In this case, it's a vector. So we want to conjoin the empty vector. In turn, it will go through each of these values and add them to the collection, and then we get the result here of a collection. I mean, it's not very useful in this particular example, but if we take all the intermediate steps that it's doing, then it's giving us the different combinations. So we've got this heads function here, which is doing reductions instead of reduce, but it's the same thing it's trying to do. It's trying to take the data and conj it into the empty vector, and so then we get the individual answers. So first of all, it generates reductions, gets the empty vector, and then it gets the empty vector plus the first value, and then the empty vector plus the first two values, and so on and so on and so on and so on. So it's a nice way to get all of the intermediary values. It's a nice way to generate a growing sequence of numbers from a fixed sequence. I hope that made sense. But that's only really, the problem is that's still only generating what I manually typed in before, because if we create a combinations function, which, oh yeah, I got this wrong actually. I got a bit obsessed with mapcat and then map concat. I just need concat on this, because what I did was just concatenate all the concatenate all these sequences together with each other, which is not good. So basically got the same sequence back again. And so then when I added them all up, they were all equal to 1, because that's what they all equal, because that's adding all these up equals 1, and I basically just recreated the original one but multiple times, so 9 times. So that didn't seem right. So actually I just wanted concat. I didn't need to map it over there, because I just wanted to put all the combinations from head and tail together, and that way we've got I think we get 19 combinations, because the tail doesn't produce the empty sequence, whereas the reduced does. So if we do combinations on this data, then we get all the combinations from head and tail. We can add them up, but even when we add those values up together, it's proved our kind of our assumption that we still haven't got enough sequences generated. So we need to try and figure out how to do that. Yeah, because we've only got so I'm adding all the combinations I'm doing. I'm mapping apply over them to just add them all up, and we get a value for each of those combinations. And then putting reduce max on top of that. So I'm going over the collection with max and just going to return whatever value is the maximum from those. So what is the maximum number from this sequence? Which is 5, but we still want 6, so we need to get more combinations. So this is the bit I haven't finished yet. So if you do have any suggestions, feel free to ask, feel free to comment. So one approach was to write a recursive function which calls itself, and varying the kind of data we passed each time. So, and I did have a little play with partitions as well. So partitions is quite interesting because you can put in a step into partitions. So we can kind of do, I wonder if we can actually make that. I think it'd be a bit of a guess, wouldn't it? So yeah. Oh, maybe actually if we do partition 4, I might actually find it. Partition 4, partition. So we're making groups of 3. So that's our partition. And then the next value is optional. You can put in a step. You don't have to. You can just put in the collection next. But we put a step, so it's how much do we jump. So even though we're partitioning by 2, we don't have to kind of go to the second value and then start making another partition. We can specify the intermediate jump, so you can create a number of sequences by putting like a step in here. So if we do just a step of 1, it's going to create pretty much all of the combinations of that particular size. Oops, that should be 4, sorry. So let's grab the, there we go. Let's paste that into there. Boop. Oh, let's do that as a comment. Oh, so actually, yeah. So this is the actual sequence that's in Codewars. If we jump back to Codewars for a second, we can see that. Yeah, if we look in the instructions, then it's saying that it's like this 4 minus 1 to 1. That's going to generate the biggest combination. So if we oops, let's go back to the editor. So I wonder if we could do, yeah, if we just did partition 4 and 1. I mean, that would solve the that one. It wouldn't solve the other ones because there's no guarantee that partition of 4 is the biggest number in any of the other tests that we've got that we have to pass, and it would be a bit of a hard-coded solution there. So one way to do it is iterate through all the different sizes of partition. That was one of the things I was thinking of, and trying to get a function that calls itself to do that. And so if we had a sort of function that calls, we need to do something that maps, that adds them all together. This is where I got a bit stuck. Let me think. So we've got let me see. So we do let's start off with a loop recur. I can't think of anything else to do at the moment. Let's do, so we want, so we've got our data, and that's going to be coming in from there. And then we've got a counter of some description. So this is quite procedural, kind of like when you're using a loop recur, it does feel a little bit more procedural because we're specifically iterating around a loop and specifying what we're doing each time. But we can take this loop and turn it into a recursive function or even a reducing function, and possibly even a transducer on top of that as well. So if we start our counter at 1, or I don't really want to counter, so like So partition size, there we go, yeah. It's just underlined because I haven't used it yet. So if we have a partition size of 1, so we initially get partition, because it might be that the biggest sequence is actually just an individual number, so like a sequence of 1. So we partition at 1, and then if we increment the partition size each time, then then we can find out, then we can like increment that until we get just empty values, I guess. And then we need some kind of value to hold the actual max value. And we'll do that as 0. I think that would work, because if they're all negative, then the value is going to be 0. So I think that seems like a sensible kind of value to start with. And then we want to do a test. I guess we can do a test to see if the data is empty, because if the we do the test if the partition size is like the same size as count. Although again, I'm a bit dubious about that, because if it's a really long sequence, then if we count them up, then it's not going to be lazy. But yeah, I think that's okay. I think we can get away with count. So if the so if the partition size is the same as count of data, then we can just return the max value. So we'll have to add, so we'll have to do some addition. So we actually have to, instead of just generating all the combinations, we'll also have to calculate the size of each one of those and put that into max value. So if the partition size is equal to count data, then we just return max value. Otherwise, then we recur. And if we use the recur function, then it's going to minimize the data that we use, well, minimize the memory that we're using, because it'll just reuse the same memory allocation each time. We go around the loop. And so we want to, and so how I usually use recur is then figure out what the data is we want to pass back each time. I think it is the same. It's the same data that we're passing. So we're recurring data, because recur is essentially just calling loop as it was a function with however many arguments we've defined here. So we've defined 3 arguments, and so we need to pass back 3 values for those arguments in the recur. What's that saying? Oh yeah. So here again, CLJ Condo, thank you very much, is telling me that fact as well. It's telling me that I need 3 sets of data. It's just so useful. So we return back the data. The partition size we want to so we just want to increment that so let's increment the partition size. So the next loop, then that will be 2, and that will create a different partition size. And now we need to, now we can go over So now we can partition all of the data that we've got, and then calculate the maximum value from that. And if it's bigger than the existing maximum value, then we can update the maximum and we return that value. Otherwise, we return the original max value. Did you get that? How do I write that? So what did I say? So we need to partition the data based on the partition size, and the step size we're always going to use 1, so then we get all the combinations. So we will get some, we might get some duplication there, but I'm not too worried about it just yet. And then we're doing it over the data, which doesn't change each time. So that will generate the partitions, but we need to wrap that. So we could use I guess we could use a threading macro, but let's just do, so we need to wrap that in, what do we use? We used map apply, did we? So when we've got the, yeah, we did the, so we want something like this then, don't we? Set the combinations is all the partitions. So we're not using head and tail anymore. We can just use partition instead of head and tail. And I think that gives us a greater set of combinations, but we need to go through, we need to increment the partition size each time. And then we'll get all of the combinations. So if we just replace the, let's do a little bit of hacking. So combinations, that can go, because that's going to be replaced by partition. I didn't need that. There we go. And then I can just slurp that in there. There we go. So we're going to generate all the partitions, and then so this is going to give us a sequence of subsequences. Then we will apply plus to each of the subsequences and add them all up, and then we will go over each of those totals and find the maximum. And then if that is bigger than if this value is bigger than max value, then we can update max value. So I guess we want another if. It's not the most elegant of solutions, I don't think, but it allows us to then refactor and make something nicer. So if it's greater, I can never remember which is greater than. I'm going to have to. So one thing that does confuse me in Clojure is this greater than and less than, which one is which. 0, 1. Oops, my editor got a bit carried away there. Oh dear. Let's try it again. Oh, go away. Sorry, my editor's going, well, no, the person driving my editor is going a bit loopy. So I think that means that, so if that's 0 and then 1, yeah, so 1 is bigger than 0. What do we want? So if, yeah, so we use that one actually. So let's replace that. So if max value, which is our local name, which should be 0, if that's less than reduce max, Not quite happy with the ordering of this, because we have to do it. I don't want to do it twice. Slurp. Do a let, I suppose. I'm sure I'm missing something kind of more obvious. Yeah, I'm going to take that in a let. Ooh. Let's put that in a let around there. Let's new. Yeah. New total. New max. Yes, using a let is a good idea, because then we can simplify this. We actually make the one thing I sometimes forget to do is put the thing inside the let. It needs to be in the scope of the let. So which is now, this is why structural editing is so useful. And so now we can use this new max here. So if I put new max in there, then the linter will be happy and it will tell me that I'm actually using new max. And it also pops up as well. There you go. Yeah, now the underscore from this has gone to tell me I'm using it. So now I'm inside, this if's inside the let binding as well, but I don't have any, I'm not returning anything. So I can do, so if it's new max is greater, then we want to return new max. And otherwise we return max value. So the existing value. Why is it not liking that? Did I spell it wrong? Oops. Boom. I must have spelled it wrong. There we go. So it even corrects my dodgy spelling as well. This is really handy. If you haven't installed CLJ Condo in your tooling, then I definitely recommend it. It will save you from millions of lots of little bugs. So that's quite involved. Again, I'm using a loop recur just to help me think through the algorithm, and then we can try and refine this later on for homework. Oh, 6! Oh! Did that really work already? That seems to have worked. That's awesome. Yeah, because we've got the data in here, so we could put this into a function fairly easily. And so let's take this loop data, and we what was our function called again? Max sequence. So, oops, give me it. So, so rather than data, this is going to be the XS name. Too many. There we go. And with a bit of luck, that will pass our test. So that passes the so that passes the mixed values, like mixed positive and negative value tests. So I've evaluated max sequence. If I switch back to the tests, we can see whether it passes this test I've got written here. It probably will fail the, well, it should fail the other tests, so, but this is the test that we haven't managed to pass yet. Let's do test all. Oh, it passed. Oh, that's interesting. All the negative numbers passed as well. Okay, that's interesting. Oh, yes, because it's returning 0. Interesting. Yeah, because I've just used 0 as the default number to return if it doesn't find a negative number. So by accident, I've managed to pass these 2 tests, but it's not actually passing the test. But there we go. But this is the most important one I got going. So this was something I can put into my tests. But if we go back, we can go and put the initial things that we had back in here. So like we had like the if condition, if statement there. So we can find that again wherever that was. Boom, boom, it's down here somewhere. There we go. Yeah, so we're using this here. Oh, so we grab this. Just a reminder of what I did. So I'm going to feed that into here, but we've got now 3 conditions. So we've got the positive. So if everything's positive, we're going to apply the data. We could probably do the same thing. Is there a negative? Oh, there's a negative. There we go. Which is probably implemented as a not pos. Let me just have a look at. I'm just curious to see how that's implemented. So we do clojure neg. Boom. And look at the source code. Just out of curiosity, I'm pretty sure that one of these will be just the inverse of the other. Oh, maybe not. Oh, it's using clojure-lang numbers. Oh, interesting. So that'll probably be some Java code, I think, that's doing that. Yeah. What's pos? Let's look at the source code for that. Oh, it is pos. Okay. Sometimes functions are defined by other clojure-core functions. In this case, it looks like we've got things in clojure-lang numbers, which is clojure-lang is usually written in Java, I think. Yeah, you can tell because it's got like numbers is uppercase N, so it's probably a Java class definition. Okay, let's switch back to 3. Boom. Okay, so we can do negative for that as well. We can do the same thing. So rather than if, we can just use a simple cond. So we can write a cond, which will take several conditions. So if boom, boom. So we apply every pred to the sequence. Then, oh yeah. So if it's that, so if that expression is true when we call it, then do whatever's next. So we could return a value here, or call a function. In this case, we're going to call apply plus on the data. I could type this in, really, couldn't I? So that goes in there. Boom. Data is XS. Let's put the cond up there. And we can do the same thing for, we'll just copy that line and then just change to neg. Oops. Instead of applying XS, we can just return 0. Boom. Because that's what it's asking us to do. And then I can get rid of this. So we've basically just turned this into a cond. And then we can just put the loop in as a default, I think. yeah, I think maybe not the most robust code, but it should be good enough, I think. Do closure cond. So we can just do else. I think you can also kind of do, I think you put your own name in there as well. I think as long as like whatever is the last keyword, then it will use that as an else as well. And then it'll, whatever, then you just use something to just generate the value or just return a value. So if we do else, and then we can just pull in the loop. Boom. And fingers crossed. Oh, and then, yeah, so the data is getting assigned XS, so that's what the data is called that's passed as an argument. It's not very pretty code, but hopefully it works. Let's get rid of the to-do. And if we're not using any external functions, no, I didn't use any of those. Let's evaluate that. Oops, let's press the right buttons to evaluate it. So many buttons. And then go back to our tests. And then fingers crossed, pass all the tests. Oh, I did, yeah. I get so excited about passing tests. Okay, now for the big challenge. Will it actually pass? Oh, let's go. That's going a bit... my auto formatting is going a bit crazy. Okay, never mind. Let's put this in. I think I forgot to do this last time, so let's just put this back into max sequence. Let's see if I can remember how to get this to paste. I think I just right click, let's paste it. There we go. That looks about right. Oh, that's done a def test. What have I done? Let's get rid of that. This is the trickiest bit, pasting it back into what have I done? Oh, I think I pressed the wrong button. There we go. There we go. That's the code I want. 3, no, 1. There we go. And if we paste this in, oh, come on, let me paste it. I'm so close to pasting it in. Let's try it again. Right, so we're going to copy that. Let's switch back to editor. Oh, I think, do I need to be that? No. Come on. You would think pasting would be a solved problem by now. Try it in Emacs mode. Yeah, so I'm pretty sure it works. It's just whether it passes all the tests in. There we go. So I've copied that. So come on, let me paste it in here. Yeah, there we go. Thank you. We got that in there. So if I run the sample test, it should pass the sample test. Yes, woohoo! And if I do all of the tests, this is where I'm not sure if it'll pass everything or not. But it might be very inefficient, so it might be slow to pass all the tests. Oh, yeah. Oh, interesting. Oh, timed out. Yes, so I think this shows that my code, while it works, may have some performance issues there, but it did pass all the tests, so that's good. Woo! There we go. So we are successful in live coding this solution, and now we just need to optimize the code. So it's very this is a very realistic, real life kind of problem. We write some code that works, and then we just need to optimize it to make it go faster. And again, we're not really using any lazy sequences here. We've used, I guess, what is essentially a reducing function, even though we haven't kind of done that. Even we haven't specified it as a reduce. But we could turn that into a reducing function. But it might be the case that we need to take a more lazy approach, and that would be a lot quicker because it doesn't have to build up so many all the combinations. So we kind of have to do a combination and then evaluate it in kind of parallel. So parallelize the whole thing. That'd be quite nice. So maybe even write a transducer. Sometimes Codewars is having a bad time. That's a good point. Yes, I can try running them again and see if they go a bit faster. Yeah, because it won't let me progress. I don't think it won't let me actually go and look at other people's solutions unless it finishes in time. Oh, there we go. Thank you very much for that tip, Mario. There we go. So if you try it a few times, then it's obviously warmed up a little bit more there. And let's submit the final just before we can, while it's still good. There we go. How satisfied are you? Yeah, it's interesting. There we go. That looks a lot simpler. Oh yeah, so we're using a using a recursive function here. So we've got oh yeah, we're using a fold here. So we've got this helper function for max sequence, and it's just using a reduce. So this max fold, which is a reducing function, which is got max here. Oh, okay, so it's pulling out max here and max so far from x, and x will be, oh, okay, so it's pulling out from, we've got this accumulator. Yeah, so this is like a reducing function here. So we're passing in a function to the reduce, and which is going to be a reducing function. We're passing in an accumulator, which will keep the which will generate. We'll use this to store the maximum here value. So the maximum of what we've calculated here, probably from the previous iteration, and then the max so far that we've done from as we're going over that, and then the excess, which is the data we're passing in to the max sequence, and then it's doing a max here. So it's setting max here to be the max of 0 and adding max here up. Then max here. Oh, max here is max so far. Max here. Oh, so then it's calling itself. No, is it calling itself? I'll have to look through that a little bit more, play with that. But yeah, this is what I was thinking of. I just couldn't get my brain around creating a reducing function this morning. I think I ran too hard on the pack run. But this is this is a nice example of like a reducing function, and I'll pick through these. I'll put these into the code as well, and decompose this a little bit and explain it a bit more. Oh, and this is reducing reductions as well. So rather than using partition, we can use reductions to generate all of the different sequences, and then just compare like the max value Oh yeah, so there's some nice ways to do this. This is a bit more like my solution, I think. So I didn't need subvec, I used partition instead of that. Yeah, so it's nice to play around with different approaches to this. Oh, there we go. That is quite a lot of code compared to somebody else's. So you can see how you can go from that to essentially something like this that really abstracts away some of the code and makes it just a simple reducing function. There's been a nice series. If you go to the Clojure Design Club, I think it is, there's been a nice series recently on reducing down. So if you'd like to listen to 58, 59 and 60 and 61, they're all about kind of going from like the basics of reduce all the way up to transducers, which are transforming reducers. So just another form of abstraction on top of reduce and reducing. So they're really useful as well. So what I was going to do was go through some examples in code in one weekend to cover these 4 podcasts. But yeah, if you've got some time to listen to them, they're well worth it. Okay, I'm going to leave it there. We're a little bit over time, so thank you for sticking with me. And yeah, we shall hope you found that useful. And if you have any more suggestions about things we can do, feel free to get in touch. And if you come up with any other alternative answers to what we've done, then let me know. I'll publish all the code on the repository we have for this, which is the if you go to Practicalli, GitHub, no, that's not right. So GitHub, Practicalli, and then there's the Codewar guides. So I'll push that up as it is now, and then I'll add some more examples of different ways to do it later on today as well. All right, well, thank you very much for joining me, and see you next time. Thank you. Bye-bye.